네, 안녕하세요. 예, 오늘 모신 나쿨 고팔란 교수는 지금 현재 아리조나 주립대학의 School of Computing and Artificial Intelligence에서 지금 현재 조교수로 있습니다. 예, 주로 이제 랭귀지 그라운딩과 로봇 학습이라는 두 가지 연구 주제를 가지고 연구를 하고 있고요. 그 다음에 이제 그런 데몬스트레이션을 통한 연구, 그 다음에 내추럴 랭귀지의 그런 것들을 통한 연구들을 주로 하고 있습니다. 그리고 이제 저와는 이제 같이 이제 박사 학위를 받을 때 이제 같이 수학했던 친구이기도 하고요. 예, 그리고 지금 또 같이 연구를 하고 있기도 해서 오늘 이렇게 모시게 되었습니다. 그러면은 okay. Now please welcome Nakul Gopalan, and then I'll give the mic to you now.
Thanks a lot. Hello everyone, so I'm Nakul Gopalan. If you have any questions during the slides, just stop me. And if I'm speaking too fast, let me know. I'll slow down. So most of this talk is about representation learning for language grounding. And I'll try to explain what language grounding is all about. But that way. Okay, thanks. Most of my problems are motivated by some sort of a collaborative situation. So in this case, you have a collaborative manufacturing setup where people help. So people work with robots to make these big Boeing airplanes in Seattle. So in most of these places, you've got these static robots working with static people because the planes are too large. There is no automation. There's not like a big robot, like a gantry-style robot that assembles wheels like in car. In car, you can attach wheels by bolting them in position. But that's really hard for you to do in planes. So in planes, you have these gantry-type system that can put these panels in. But if you try to get this gantry, then you can't have people. So either you have people working by themselves, or you have these big gantry systems where where only the robots work and no people. So this is a project that I did while I was a postdoc at Georgia Tech. And here we were trying to teach how to insert the same panel with the human user giving demonstrations, and then the robot just figuring out with reinforcement learning how to do bolt insertions into panels. So the tolerance here is less than 5 millimeters. 0.5 millimeter tolerance between the bolt hole and the bolt itself. And so it's learning from demonstration for the reinforcement learning policy. But apart from that, there's a whole bunch of SLAM to localize where the panel is and where the bolt hole is and all that. So it's a fully robotics heavy problem with some reinforcement learning going on just for bolt insertion policy. So I think that this is the way you will have companies working in the future, where some human can teach the robot how to do something, and then the robot will learn how to do that along with the human user. So in my dream situation, this plane, when it's being assembled, you'll have a human that will say something like, attach the panel to the seat track. And then the robot will be like, what is a seat track? It doesn't know what a seat track is. And then a human might show, this is a seat track. The robot will be like, what's the policy with which I'll attach the seat track? And then the human will demonstrate that I attach the seat track like this. So it's a very collaborative learning approach between the human and the robot. So generally, the way I motivate my talks is that I want to enable robots to interact, collaborate, and learn naturally with people. And naturally, I'm just using this is the Macmillan Dictionary definition. It just says, this is how people would generally do it by themselves. So it's how people would expect or understand a particular behavior. Okay. So first, I'll just give you a quick pitch on what language grounding is. This is a really old idea. If a human says, clean the table is that object in the world. It's one thing in the world. Okay, so the table, this word, is a symbol. It's very crisp. It's a symbol. It's referring to an object that's continuous. It has some weight. It has some density. It's made of molecules. It's very continuous. And symbol grounding is mapping this discrete word that you have to some continuous context in the world that the robot is seeing or feeling. So this was defined by Harnard in 1990. I have a paper that's specifically about this problem in a robotic situation that came out in 2020, where we're just talking about why this problem is so difficult for robots. But to give you a quick pitch, language is structured. You can make a parse tree out of it. It's got a very structured representation. But real world is cluttered. What the robot is perceiving is continuous and noisy. You don't know which object is in front of what object. It's just noise. Language is discrete. The real world is continuous. Language allows for high-level reasoning. So if you look at the sentence, it says John hit the ball. But robot doesn't understand what John hit the ball means. The robot's just seeing a continuous time position of the robot's arm, and where the ball is, it just does not know what that sentence means. So the robot is all about low-level control and observation, nothing high-level. But language is all about high-level reasoning. So most of my gap tries to bridge this gap with what I call representation learning. I try to learn representations that help the robot understand how to bridge the gap between language and the continuous thing that it's seeing right now. Okay. The other problem that you run into in this type of problems is that humans can only give a few demonstrations. So my friend Michael here basically gave only one demonstration. He can maybe give 10 demonstrations, but he can't give 1,000. He can't give 1,000 demonstrations. He's not that strong. So I want to learn, and the other problem is that there is no general purpose corpus. It's not like there's a big data set of humans reacting with people. So there's still this problem of sample complexity where collecting that data set is hard, and you can't just apply regular deep learning to just make that work. So I try to address this with some efficient machine learning methods which have some structure, and I'll keep talking about the word structure here again and again, where we'll take a problem and we'll add some structure into it so that then it's easier to learn that problem. And again, we use like classical tools like mapping and planning that most of you will be familiar with. So we try to learn things so that then we can do mapping and planning with them. Okay, so generally the areas of research that I work in are mapping language to some pre-specified predicates. And I'll talk about that in a minute, where there are some predicates and you're just mapping language to some known predicates that you've learned previously. The other problem is representation learning for objects. I'll give you a small taste of what that looks like. I'm also working with June, who works with you. I'm working on an object learning problem with him right now. And then there's this problem of behavior learning, where you try to learn some sort of behavior on the robot with language. Okay, so let's start with mapping language to some pre-specified predicates. Oh, okay. So in this demo, I'm asking the robot to do something. So in this case, I told the robot,
drop it into the bin and repeat.
the volume is too low, but I'm asking the robot to search the table for a cube and drop it into the bin and repeat. So in this behavior, if the robot sees a cube underneath its search pattern, then it's supposed to pick the cube and put it in the bin. If there's no cube, then it should continue searching. Okay? The problem with this is that it's a continuous behavior that should keep on going to infinity. The robot's never supposed to stop it. I didn't say stop after the first cube. I didn't say stop after the 5th cube. And you can have other constraints here. You can say put only the red cubes, but not the yellow ones. And the robot is still supposed to follow that. So these types of problems are really hard because they don't have a single goal condition. You're specifying some continuous behavior that the robot needs to do forever. And if you're familiar with reinforcement learning and things like that, reinforcement learning generally has a discount factor. It has a horizon of 100 steps or something like that. This kind of behavior doesn't. It just says keep on doing, which is like weird for a robot to keep on doing. So in this case, we were specifically trying to move beyond what we call end goal specifications. We wanted the robot to do something that's a continuous behavior. So another example for this is when you tell the robot to go through the yellow room to the blue room. So in this case, the robot's supposed to go through the yellow room to the blue room. It's not that the robot is just supposed to get to the blue room. There is a constraint specified in that trajectory. So if you try to do this directly from language to trajectory, you need a lot of data. So how do we avoid collecting all this data? We provide some sort of structure. And what that structure looks like is the idea of linear temporal logic, which has been known to roboticists for a while. So what we do here is we specify some propositions, and then we map language to those propositions. We don't map it directly to trajectory. And then we use those propositions to specify a behavior to a planner, and then the planner will plan. So in this case, in linear temporal logic, you have some proposition. Let's say F is finally. So you have some proposition Q. This proposition Q might say that the robot is at home. So when you say finally home, the robot needs to be at a state when it's at home along the trajectory. If you say globally safe, then you're trying to say that the robot needs to be always safe. It needs to be safe at all points in the trajectory. If you say in the next time step the robot needs to be safe, then in the next time step the robot needs to be safe. If you say that the proposition P, so it needs to be safe until it gets home, then the robot needs to follow that behavior. So once you can write down the propositions, the propositions in linear temporal logic, you can then give it to a planner, and then the planner can then generate the behavior that the robot needs to do to get to satisfy these commands. So in our case, we took this language command and we converted it into an LTL expression. So go through the yellow room to the blue room now looks like finally be in a state where you're in the yellow room and you've also been in the blue room. Okay, so for this we collected a corpus. So this paper is very old, it's from 2017. So we collected a corpus where we said go through the blue room, and people would tell you whether this is the correct behavior or this is the correct behavior. They'll basically put a check mark on Amazon Mechanical Turk. And so we collected a whole bunch of language to the right expression and the trajectory data online on Amazon Mechanical Turk. And so we have some example commands that go to the green room might translate to finally go to green kind of commands. And then we basically used machine translation. So this is like the first attention-based translation mechanism that was new in 2017. So we translated like natural language to some sort of like propositional language on the other side, and then we specified it to a planner, and the planner just planned to get those behaviors out. Okay? So then we can get these types of behaviors out on the robot where you say go to the yellow room go through the yellow room to the blue room, and the robot is basically taking the planner specification that is specified by this natural language command, and then just planning. Go to the blue room through the green room. So in this case, it's really interesting. The robot can't really turn in this room because if it turns, it'll hit the blocks. So it figures out that it has to go to the other room to turn around because of physical constraints. And you can do that because you've got a planner that's planning, and it's not just like a reactive trajectory that's just functioning on the robot live. So that work was all about mapping language to some pre-specified predicates. But now I'll talk about representation learning for objects. So over this talk, I'll get in more and more details about like topics where learning is involved, because I was told that all of you guys care a lot about learning. So a lot of these talks would concentrate on learning for objects and learning for the behavior on the robot itself. And then maybe we can have a discussion about older style methods that I still work on. So in this case, we're talking about object-centric representations. So the world is made up of objects, okay? So when we say that go to the green room in that case was an object. You said that that's an object that you need to behave with. So can we learn characteristics of objects with language or with the physics with which we're working, with which we're interacting with the object? So one of the first papers that I wrote in this area was to learn object shape attributes with language. So what we tried to do here was, what we tried to do here was, you wanted to, so if the object that you're interested in has a physical 3D shape, right? So objects are not just 2D. Objects have a 3-dimensional space. The reason why that 3-dimensional space is important is because the view to a robot is partially observable. So to this robot, when you say pick the couch with no arms or pick the couch that is of L shape, it's actually making that decision from a partial view. It can't really see all the arms. It can't see all the legs of the couch. So it's not just a plain visual classification problem. And we show that in the paper, that the 3D data is actually useful for the robot to classify these objects. So for this, what we did was we embedded the depth image of the robot into an object embedding model. So this could look like you take the voxel data of the image that you get from the camera, and then you embed it into a deep learned space. So that's a high dimensional space where you've embedded the 3-dimensional data that you captured from the object. Then you've got an embedding for the natural language. And then you try to force both of those embeddings to be close to each other with respect to some cosine similarity metric, right? So you can take, so this embedding now is a joint embedding between the language and the object embedding, where both of them share the same space. And in that space, you can say, if a couch has no arms, then that couch is close to some 3D shape that you can physically classify. So again, so this is like a quick demo for that, where you say pick the couch with no arms, and the robot's able to do it. So the next project that I worked in this area was about learning object representation that's based on usage. So in this case, we cared about objects with respect to the verbs with which objects are specified. So if you say, give me something to wear, only one of the objects here is a cloth. None of the others are cloth. Now, to you and me, if I ask for something to wear, you know that only clothes can be worn. But the way robots think about objects is generally in the physical space. It's not in terms of the affordances of the objects themselves. So the affordance is how an object is going to be used in the future. And so in this work, again, we try to learn something about the object, given some natural language commands that specify the usage of the object. So in this case, we collected, again, a corpus that has a whole bunch of natural language sentences about objects that say how the object is going to be used. And then the pipeline, if you look, it looks very similar to the previous 3-dimensional object pipeline. We have the RGB image, we've got a natural language command, and we're kind of learning a cosine similarity-based embedding space where both the object embedding, the object image embedding, and the natural language embedding are close to each other. So when you specify, give me something to wear, out of the 4 objects, only one of the objects is actually close in that embedding space to the natural language command. So we ran this on the robot again, all real time, so you can tell it to wear something, and it's getting like real time feedback, and it's trying to process which object to wear on that demo. So I really like this one because all the objects are slender and narrow, but it's able to learn it in a refined enough way where it knows that a pen is a pen and it's not, like the knife is not close in that space. And in one more demo, we asked for give me something to cut, and the spoon was the only object with which you could cut, and it will pass you the spoon. And the reason why it does that is because it's paying attention to what objects have sharp edges that can be used to cut. So there's some generalization in these types of pipelines to generalize to objects that haven't been seen for that type of use case. Okay, so in this case, what I'm trying to say is that the world is made of objects, and we're trying to learn characteristics of objects through language. So those characteristics could be in 3D shape. Those characteristics could be in the affordance of the object, the verb that specifies the use of the object, and we can still learn the mapping between language and the object that specifies those types of criteria, whether those criteria are verb dependent or those criteria are physical shape dependent. Right now, June and I are working on an object-based kinematic model where we're trying to predict what an object is capable. So the fact that this bottle has a cap, and the cap has a kinematic model that's attached to the bottle, so I can unscrew it. We're trying to learn things like that. And we're also trying to learn where should you apply the force so that the object actually changes the current state. So in this case, I should apply the force to the cap, and I shouldn't squish the bottle. Squishing the bottle is not going to lead to it opening it by unscrewing. So those kinds of physical properties are present in the object's kinematic model, and we're trying to learn that property right now. Okay, so I'm sorry, slides are coming up weird, but the third area of my research is representation and behavior learning. And here I try to learn representations for planning. Okay. So in the first paper in this area, the objective is to teach a robot with language and demonstrations. So you tell a robot to go straight and take a right, and you collect the trajectory for it. And with this, I want to learn, with these types of paired demonstrations, I want to learn how to specify natural language command for a new task that the robot might not have seen. Okay, my real problem is that I want to teach this on the robot. I can't really do this on a simulator. So how do I teach this behavior on the robot in real time with like a few number of demonstrations? So here I'm going back to the question of sample complexity, the fact that I can't collect a lot of samples about the behavior that I want the robot to know. So the way that I try to attempt this problem is with structure. So I don't try to solve the problem in one shot. I don't try to go from trajectory to language again. And I'd done this previously for my work in planning, so I used the same kind of insight that maybe we don't need to go from language to trajectory, like a deep control kind of behavior. Maybe I could break the problem into smaller subsegments and solve those smaller problems. So the problem number one here is you would notice that the behavior has going straight, then taking a right, and then going straight. Okay? So maybe you're giving a lot of demonstrations to the robot, and there's some similarity in those demonstrations. So maybe there's a way to measure that similarity, right? So can we demarcate this long problem into smaller problems and then solve those smaller problems one at a time? If we can do that, then what we can probably do is take the natural language command and then map it to this idea of going from behavior 1 to behavior 2 to solve this natural language command. Okay? So the first step is break a long trajectory into smaller repeatable subsegments, and then the second problem is to map language to those smaller subsegments. Okay. So what we try to do this is, the way we try to do this is we collect like the raw action data on the robot, and we pass it through classical change point detection pipelines. So change point detection is an unsupervised technique to break a long trajectory into smaller segments. People in robotics have used change point detection for a while. So generally what people do is they break apart actions and they try to learn options with it. And there's a whole history of this work where people have attempted to do this. Then we collect the observation that you see at the end of that, those options or skills that you might have learned. You collect the observations, and then you can use those observations to learn a classifier. Okay? And then you can translate natural language to those classifiers, and then you can just run the classifier on a planner that will split out actions. So what I'm essentially saying is that you can collect a long trajectory. You can split the long trajectory into smaller trajectories. For each trajectory, there is a termination symbol. The trajectory finished at some point. You can collect all those termination states. You can learn a classifier around them. You can be like, okay, when you go straight and stop somewhere, this is what the world looks like. If you stop next to the table, there's a table in front of you. So let me just collect a state where you're next to the table and learn a termination classifier where your planner will finish planning. Now, if I have a whole bunch of these classifiers that can classify termination states, I can, given a natural language command, I can have a sequence of these termination state classifiers, and then I could plan to those termination states. Okay. So when we were collecting data,
first, the robot is given demonstrations of how to do a task while we record the sensor data and actions. Then the demonstrations are paired with language commands. In our experiments, we crowdsourced from Amazon Mechanical Turk.
So we collected about 70 demonstrations of the robot being driven around Brown's campus. For each long video trajectory, we uploaded it on Amazon Mechanical Turk. And then we collected natural language commands for each trajectory, right? So look at this natural language command. It says, go to the water fountain, then turn right, and then head to the door. So each segment is already, in language, people are already breaking down the trajectory into subsegments. And then we're trying to learn the mapping from that language command to the subsegments that we learned using change point detection. Okay, so at the end of subproblem 1, when we learned those classifiers, so this is just like a visual demonstration of what those visual classifiers look like. So you can see that the end of the corridor symbol that we learned, the robot is right next to a wall. So it's almost like you can see that the LiDAR data is showing that the robot's next to a wall. And when it's turned right or left, the robot's just seeing an open corridor. So then we learned 5 symbols with the robot data on the robot, and then we translated about 1,000 natural language commands to novel behavior that the robot hadn't seen before. So you can learn just with 70 trajectory about 5 symbols, and then you can specify novel behaviors that could be longer than the behavior that was specified for the robot previously, and then you can just plan. So in this case, because we have language, we had a paired corpus of natural language and these termination states that were observed at the end of this natural language. So we also learned a translation mechanism. This was just a really simple sequence-to-sequence kind of pipeline back in the day. And then we just use motion planning, you know? So
we further demonstrate
demo.
the power of our model by converting complex natural language sentences into long sequences of symbols.
So the thing that I want you to understand is that when I collected these demonstrations, it's a Movo. Yeah, it's a Movo. Yeah, I saw your Movo. It's really funny. I know how to hack on that thing. If you have questions, like, yeah, it's not a nice robot. It has lots of issues. I mean, all robots are bad, but this one's also bad, is what I'm saying. So the demonstrations that we collected were around 200 to 300 seconds long. This demonstration, the demonstration that it ran was longer than 1,000 seconds. It hadn't seen this corridor. It hadn't seen this corridor. It hadn't seen this natural language command. It can still plan because it's not learning mapping language to some trajectory. It's learning the mapping between language to some sub-goals that it can plan to. And then it knows what sub-goals to plan next. So most of the papers that I've talked about until now are papers at RSS, including this one. And there's very little learning going on in most of those papers. What we have done is we have taken a large learning problem and we have broken them down into some structured problem that we then learn. But we're only trying to learn like small bits of it. The problem still is that in most of those problems, you still have to teach the robot everything that the robot's seeing in front of it. It's learning on the fly in the real world. And maybe you don't want to do that, right? Maybe you don't want to teach the robot everything. So what do you do then? So in this case, in this specific work, we separated the robot learning problem from the language grounding problem. So language grounding is how do you take language and map it to a symbol? And then robot learning is how do I get the continuous trajectories out? So maybe we have a pre-trained pipeline that spits out pixel-wise policies for the robot. But now that pixel-wise policy is some deep policy. How do I map language to that? Because until now, we had mapped language to some discrete tokens that we had learned or specified. But now we're trying to map it to continuous policy parameters. So in this case, there's a 3D scene that the robot's observing. And the task is to create a stack of objects. So what we can do, so we already have a neural network that specifies pixel-wise Q values for pick and place. So to build a stack, it knows where the right position for grasp is for a particular object. Okay? So it knows what the right Q values are, but what it doesn't know is any preference. You can't say put the yellow block on the green block. It doesn't know how to do that. It just has a whole bunch of Q values. And the robot, to do any stacking, just takes the highest Q value and does the stacking, right? It just whatever pixel has the highest Q value, let's just pick the object over there. Okay. The problem is that we're trying to map language to these continuous policy representations that you've already pre-trained the robot to do. So again, block arrangement is a classical planning domain. Most of us who have taken AI courses have looked at the Tower of Hanoi or something like that. It's got the classic resonance. We now have robust pre-trained models to solve these types of problems. And we're trying to see if we can map language to these pre-trained models to solve novel tasks. And it's difficult because you don't want to retrain your policy model. The policy model is already learned. So the way we try to do this is, we try to reuse the policy that's been specified. And the way this domain works is there is some state of the world. So in this state, you say stack the blue block on the yellow block, and the result of that will be so the robot picked up one of these two blue blocks, put it on that yellow block, and then now you say stack the red block on the blue block, and it'll pick one of these two red blocks and put it on the blue block. So it's natural language-based stack making, right? Okay. So for this, we have two types of data sets. So one, we created our own programmatically generated 3D data set with language and 3D visual and policy data on a simulator called Copella Sim. I don't know if any of you use it over here, but it's really nice. The physics is really good on that. Then you can see the UR5 over there. But we also ported the 2D blocks world from like a Jonathan Bisque data set from 2018. So this was a 2D data set. We ported it to 3D. And so in this, the data set is weird. You say some things like Mercedes-Benz will move right until it's over Twitter. So you can see that each of these tiles has a company token on it. So this is McDonald's, there's Toyota, there are a whole bunch of, this is Twitter. So you need to move Mercedes-Benz until it's over Twitter like this. Okay? this data set is public. You can use it if you want. So then you move those two. You move these two to make a system like this, right? Okay. So how do we do this pipeline where we are going from something that's discrete to something that's continuous? So in our case, we've got an input image. The input image is a 3D image, and we've got an input language command. We've got a pre-trained policy network. So this is a spot queue network, but if any of you are doing just SE2 pick and place, then you might be familiar with transporter networks. It's a deep learned policy network representation. It's similar. It just gives you a Q value on the 3D pixel space. And that's all that's going on. There's nothing special about this. Now you'll notice that the pixel value, when you say stack the red on the blue, the highest pixel value is this one. It's this green block. And there's a reason why it has the highest Q value. It's really far away. If the robot tries to pick it, it can pick it up very safely without disturbing any of the other blocks. So that's why it's learned that the Q value in this pixel is really high. But you don't want it to pick this green block. You want it to pick this red block, which is over here, which doesn't really have a high Q value, right? Okay. Then this was one of the first image language transformer network papers that we wrote. So this is like, that was published. So this is like directly after the vision and the VILT paper came out, the vision language transformer network paper came out, where you basically take like an input image, you break it down into a whole bunch of patches, and you take the natural language command and you feed both the patches of pixels and the natural language command into a transformer network. And what you try to do is to predict a patch-wise mask. So what we're trying to do here is we've converted this problem of picking the right object, which is in continuous space, into a classification problem. Here, we're only predicting the right patch. So in this image, it was a 4x4 image, so it's only a 16-way classification problem to predict the right patch. Right? Once you've predicted the right patch, you look at the 3D data underneath that patch and you can rotate it along with the orientation of the original object. You apply this pixel-wise mask back to the original image that you had, and now you get this newly reformulated, rescaled Q value. And now you're picking the object at the location of the highest Q value, which is mapping to the red object. Right? So again, we use the structure in the problem to convert something that's continuous to a discrete choice in a tabletop setting, and now we're able to pick up this problem. We're able to solve this problem in like a straightforward, discrete way. So again, this is a pipeline. You split the image into, I'm sorry, this is 9x9. Okay, so it's 6x6, so it's a 36-way classification problem. And you have the language and the transformer data that's patch-wise, and you feed them both to a shared transformer. The detail that I didn't tell you was that we have two classifiers, one for grasping and one for placing. So it's two 36-way classification problems for grasping and placing. Your agent can decide whether it wants to grasp right now or whether it wants to place right now. So if you're doing math prediction, it's just binary cross-entropy loss. It's really simple to do. And we have some auxiliary losses to make sure that we're predicting the right block and stuff like that. So what you can see is that we were beating all the baselines that existed until then, whether you use plain reinforcement learning. At that point in time, to learn a pixel-wise mask, the existing baseline was UNIT, so everyone was using UNIT. And at that point in time, this is just 2021, so it's not even 2 years old now. But so everyone, so we were doing way better than UNIT then, and so we were able to build rows and stacks with this type of with the same type of pipeline. So we also did a data ablation study, and we were trying to show a trend where if you gave more real data to the image, right? So so the learning that happened in this case was purely in simulation, and the sim to real transfer is almost zero shot. But if you gave more real data to the agent, we were able to show that our pipeline generalizes better. So this is like what's called like an idealized placement score of like whether the robot is picking up the object at the right pixel. So we're measuring it at pixel level accuracy. And so in this case, what we're trying to say is that the more real data you give it, the trend is going down. So the agent is learning how to pick and place objects better the more real images it sees, which is nice because if you put this robot on a shop floor, it'll keep seeing more real data, so it'll get better over the task. It'll get better at the task over time. Besides that, we had real demonstration results on the BISC et al. Data set as well. Cool. So one problem that I care about a lot is compositionality. And over here, we're trying to see if we can generalize from pick red and place blue to pick black and place green. Sorry, I've shown you pick red, place blue, pick black, place green. Can you generalize to pick red that you saw over here and place green that you saw over here? Right, so I don't want to show you all sorts of combinations in which natural language commands will come. Can you generalize from the data that you've seen previously? And what we notice is that we get way better compositionality results than we had gotten previously from other pipelines. So what we did was we held out like 26% of the data, and we get really high accuracy on those data sets. And UNet doesn't do anything close to that. So again, this is like a standard demo for the thing to show you that it actually works on the real robot. And what's really great about this is that it's a continuous policy. So it's a continuous visual motor policy. So if the robot slips, if the robot can't pick up an object, it'll keep on trying because it's a visual motor policy, right? So it's not like a planner where the planner failed, then the planner might not know that it has failed. There's no visual feedback that's coming to the planner again and again. So in this case, even if it fails, it kind of recovers from there because it's a visual motor policy. So we found this to be pretty robust. Like it keeps on trying until he gets it and keeps making the stack. Great. Okay. So then the other problem that I'm trying to answer with my group right now is how do we pre-train these skills? So you have some pre-trained skills. How do we keep getting those pre-trained skills? And another thing that we're looking at is structure. So in this case, in previous pipelines, I've used change point detection, which is an unsupervised learning method. We're trying to flip it and make it into a long trajectory. And somewhere there was a language command that said make pancakes, and the robot made pancakes there. Then somewhere else, you should be able to know that you can repeat the task of making pancakes in some other task specification. And the reason why you can do that is because now we have a lot of language and trajectory data. So can we now try to do this in a supervised way where we don't have to learn these these subtasks in an unsupervised way? So in this case, we've got a language command that says examine the vase by the lamplight, and there's a sequence of language instructions for it. So to do this examine the vase by the lamplight, you might say turn around, go to the desk, pick up the yellow vase, turn left, take a step, turn right to face the lamp, and turn on the lamp on the desk. So this is the data set that already exists. It's on the Alfred data set. And this is what the video for that looks like. So the agent is turning around. It's going to look at the desk. It's going to go to the yellow desk. Then it's going to like pick up. It's going to pick up the lamp, and it's going to turn it on. So this is like a very first-person view. And what's really nice about this is that there are, this corpus has more than 10,000 trajectories like this that were collected on Amazon Mechanical Turk. So previously, again, I've already shown you in my thesis, I used the unsupervised change point detection framework, very common in robotics. In this case, there's a related problem on YouTube. So in YouTube, if you see there's a long clip, people are doing different things, and you say, I want to see the part of the clip where the person is flipping pancakes, then YouTube can actually find you the part of the clip that actually has the person flipping the pancakes. And this problem is called moment retrieval from videos. So it can retrieve like one particular moment from that video. So our work is actually trying to do that. We're trying to retrieve the moment in the robot trajectory where that thing is happening. And for this, we have like a we have a feature generation pipeline where we try to generate like features from the video. There are two types of features. There are clip-based features, which take in both the language and the video, the image frame based features. And then there's like slow-fast features, which are like specific features just for video trajectories. And then we have clip features on the discrete actions, the actions that the robot is taking in the world. Our architecture is really convoluted. There's a lot going on over here. There are trajectory features and some natural language instruction features. Again, there are transformers, so you encode this into a linear layer and then into a transformer. But what we're doing is we're trying to measure saliency scores. So we're trying to measure when a particular natural language command is close to a particular set of image frames. So some natural language command is specifying some image frames, when are they close to each other? And we're trying to do this with like a supervised saliency score metric. Then we're trying to classify the entire sequence of image frames into background image frames or foreground image frames that you care about or image frames that you don't care about. So it's a binary classification problem. So you took a unsupervised change point detection problem into a binary supervised versus unsupervised problem. We have a whole bunch of like intersection over union and L1 losses for detecting the moment at the right place and things like that. What we basically show is that even if you just take the video features and retrieve it directly on video, you get like 83% performance on 0.5 on IOU. So 0.5 on IOU is saying that the intersection over the true part of the segment that detects the trajectory specified by the natural language command, and what you detected is at least 0.5. Okay, the intersection over what you detected and what really happened was at least 0.5. So this is pretty impressive because this is basically state of the art for just video retrieval. And you get that immediately on the robot, even if it's just on simulation. As soon as you start adding robot data, you get like 2% improvement on robot data with contrastive learning. I think that these gains are not very great. I think that this gain with the robot action data needs to be pushed up. We also did a whole bunch of like ablation studies. So we saw that even with 10% of the data, with just 1,000 trajectories, you get about 50% performance on these metrics, which is not terrible. So maybe that much training data is enough to improve your performance later. But it's also not very good. Like, it's not good for sample complexity. I can't collect 1,000 commands on the robot. So we're still looking into this method and trying to improve it. Okay, so there are a whole bunch of research areas. I'm trying to finish my talk now, and there are a whole bunch of research areas that I have not gone into in this talk. One is collaboration. So there's a human talking to a robot where the human says attach the seat panel to the seat track, and the robot goes, where's the seat track? So I didn't talk about dialogue at all. Then there's work in human-robot collaboration. So in this case, I'm specifically studying how do people teach robots. So this is almost like a cog-sci kind of question. Like, what kind of behaviors do people teach robots when they're trying to teach them? So in this case, what we have noticed is that people generally give low-level demonstrations to the robot. They like to hold the robot's hands and tell it exactly what to do, but they don't use these repeatable subtasks. They don't say go to the cup so that you can pick up the cup repeatedly. They don't give demonstrations like that. They give like low-level, complete trajectory demonstrations, which is not very good for learning like repeatable skills on the robot. And the other thing that we've noticed is whenever people try to teach subtasks to the robot, they don't teach it correctly. So what we've noticed is that there's a correspondence problem in teaching abstractions to the robot. And then in our recent work in RSS 2023, we noticed that curriculums actually help people teach robots. So you can build a curriculum for humans so that they get better at teaching robots. And those curriculums are all about how should you teach the robot over 5 different tasks or 10 different tasks. So it doesn't matter what the order of the curriculum is. It's just that people get familiarized to teaching robots and then they learn how to teach them correctly. So you can get people to teach basically task and motion planning based primitives directly to the robot if they've seen enough task and motion planning problems. This question is still unanswered. We do not know what type of curriculums are good for people. The other work that I did in human-robot collaboration is dialogue. So in if you imagine any human working with a robot, they're probably going to try to talk to the robot. And so you want the robot asking for help. So in this case, I actually worried about whether the robot is actually confused or if it's uncertain about certain things. How does it actually model uncertainty in that case, right? So this is a complete POMDP problem, but it's a dual agent POMDP problem where the human has something to do and the robot has something to do. But what I've noticed is until now you need a model of the task. You need to know exactly how the task is going to proceed. And that's not sufficient. That's not a very good way to teach the robot because you can't have a model for every task that a human might want to do with the robot. The other thing that's missing is this question of what is a seed track, because that goes back to representations. So there are other work where I'm specifically looking at just representation learning for the sake of transfer. So if I show you the stacking task and the rowing task and the unstacking task on a robot, can I generalize to a vertical square task that you've never seen before? You don't know how to do this task. How quickly can you generalize to this? So we have noticed that generalizing to unstructured environments is necessary. In this case, we've been able to do it through pre-trained policies. But then we go back to what type of pre-trained policies we need to do this sort of work. Because all of this is in simple blocks world kind of scenarios, and we don't know how to generalize to non-blocks world kind of scenarios. The other work that I care about is compositionality. So when I say go to the red chair, the concept of red has nothing to do with the concept of chair. Red is a color, chair is a shape in the world maybe. It has other functional properties, but red doesn't affect it. So this work, I have an ongoing collaboration with Benjamin Rosman's group in South Africa, where we work on learning compositional policies on reinforcement learning. So here you specify pick up the red ball, and what we want is we want to learn a policy for pick up red and pick up ball. The problem is that we don't know in advance how many of such concepts will exist, but we want to learn them compositionally. So right now we're doing it by a transformer-based approach with the curriculum learning-based approach where every time you learn a new type of compositional concept. So either whatever behavior I've specified can be done with your bag of compositional concepts that you know, or you need to learn one more to solve the problem. So we are slowly adding compositional concepts in a curriculum way, one after another. The other work that I'm working on right now is just learning representations of tasks when objects themselves are not known. So if you go to a robot and say, this is how I build a house, and then you say, this is a red tile, and then you want to say, build me a house with red pillars. And so the robot needs to understand that what I'm asking is, I'm asking this red object to be used as pillars of that house. And this is more like an AI kind of problem, where we're basically trying to learn what functional properties do objects have and how they get used in visual task solving. We actually have a functioning robot demo. This work is in the status of user study. So we're actually doing a human subject user study where we're trying to show that people are actually happy working with this robot in this type of task solving scenario. So overall, my work is in teaching tasks directly on the robot. I try to map language to behavior on the robot. Sometimes I use pre-trained policies to solve novel natural language commands. The larger problems that I care about nowadays is dialogue, compositionality, and feedback. How do you get feedback from the human for the tasks that the robot's doing? I work with a whole bunch of people. June's right here. Thanks a lot. If you have any questions.
질문 있으신 분 있나요? 예.
Hi, thanks for your talk. And in the second part, in the object-centric representation, and in the close example, how does the robot contribute to the learning of the affordance of the clothes wear? Did you get it?
So the robot doesn't. We collected a Wikipedia corpus where we collected, I think we collected like 100 objects, and then we went to the Wikipedia page of that object, and then all of this was like automated corpus collection. We basically looked at what verbs were associated with that object. Then we collected images for that object directly. So, excuse me, this whole problem of affordance can also be told, like, where do I grasp this object is also an affordance. Like, do I grasp it here? Do I grasp it here? Do I grasp it here? That's called grasp affordance. We're not learning that over there. All we're learning is which object is used for what purpose. The other work that I'm doing with June right now, over there we actually worry about how do you actually modify this object so that it gets to a state where we want the object to be in. So if I want this bottle to be open, I probably want to unscrew this cap. And so for that, we need to know the model of the object, like what can be unscrewed and what happens after you unscrew it.
Thank you.
You're welcome.
And one more. At the before that example in the couch without an arm example, then because robot has partial observation of that couch, then when the robot picks up the couch without an arm, the robot needs to turn over the couch or?
No. So what we did was to learn the object embedding. We took 360-degree scans of every object. So in that problem, what we're trying to do is, because the robot has seen couches from 360 degrees, can it then generalize from just one view of sides that it doesn't even see? So humans do this all the time. Like if I asked you to go to the long couch or something like that, you might even see a long couch from far away with one view, and you'll be like, that's a long couch, I'm gonna walk to it. So we were trying to do that. And the only reason you can do this is because you've seen a lot of couches in 360-degree views, so you have a good model of what a couch looks like.
Got it. Thank you.
You're welcome.
So thank you, Nakul, for your good talk. It was really great hearing a lot of work that you did. I just have one question. So there are a lot of people who are actually using LLMs in solving a similar task. And I saw a lot of your work based on how to come up with a structure to learn all of these things.
Right.
So could you tell me how is it different from the LLM work that other people are doing, and how where your work is going to go next?
So there are people in my group that are also working on LLMs. So what people are using LLMs right now is they're using it to specify. I'm sorry. It's not a problem. I'm trying to. Oh, it's not being shown. So what people generally do is they ask the natural language, they take the natural language command and try to spit out a specification that looks like this. So when you say, so if any of you have seen the SCAI work, what you try to do is you tell the robot to go through the yellow room to the blue room, and the SCAI pipeline will say, go to the yellow room, and then the next action will be go to the blue room. And then there are continuous control policies on the other side that have been pre-trained, and they're mapping each of these tokens to the continuous control policies one after another. So the reason why Google can do that is because they've got a huge bank of pre-trained policies. In robotics, we generally specify these behaviors as planning because then I can specify a goal condition and then I can just plan to that. So in some ways, you could have done that work back in 2017 or 18, whenever this paper is out from, because all you're doing is you're specifying the next condition that the robot needs to be at, and you've got a value function for it. What's special about LLMs is because they've read so many textbooks, they don't need a symbol grammar. So over here, there's a symbol grammar that I have given to the translation pipeline. I've said that finally, and then there's a token yellow, and then finally, and then there's a token blue. It has read so many textbooks that it knows that going to the red room is a thing, and then going to the blue room is a thing, right? So that kind of specifying of the next subtask is a great power that LLMs have that they have learned from reading so many textbooks. So that works really well while it's working. If it doesn't get any feedback from the environment, then it can fail. So if you've looked at some of their demos, the robot can fail when it's doing these things because if the policy doesn't do what if the policy didn't do what it was asked to do according to the LLM, then the policy might just have to break and a human will have to come and intervene and fix it. So I think LLMs are great. Like, I think that people should be trying to spit out task and motion planning based plans using LLMs. We still haven't managed to close the loop. And the larger problem still is how do we learn these underlying skills? So how do we learn what yellow and blue are? How do we get to the yellow room? What does the policy of that look like? So getting to the yellow room is like an easier example, but opening this bottle is a much harder one because it's bimanual manipulation. So how do we learn these types of bimanual manipulation skills and dynamic skills like throwing and catching? How do we learn all those low-level skills so that you can map whatever the LLM is saying to that? So skill learning is still a big pipeline for us.
Thank you. Thank you.
I think my question will be related with your answers. Maybe first clarification questions. I think slide 28 or something about the grounding between language and vision. 28 or 27?
Yep, that was 28. So it's 27.
2 column. Oh yeah, that picture. So basically, you want to ground the linguistic objects into the visual, right? Image and language. Do you have here already some pre-trained model?
No.
Otherwise, how?
This is like much older. This is 20. So we didn't have any pre-trained ImageNet or anything. No.
So
actually,
here,
they did
the
have
image
a ResNet.
and
So
the language.
So this has some image data.
Oh, okay. Oh, yeah. Right. In the ResNet already, I mean, how the language is combined with the vision in some way before. Otherwise, how can we embed into the same space?
So
two embedding space might be very different, but actually we want to have some correlation between those spaces.
So this is a learning problem.
Okay.
So we specified, we gave the algorithm some RGB images, we gave it a natural language command. From the natural language command, we extracted a hidden layer that's 64 dimensional.
Exactly, yeah.
From the ResNet, we extracted like a 2048 dimensional embedding. Then we forced this 64 dimensional embedding to also be 2048.
Basically, you want to make them similar, right?
We forced these two embeddings to be similar. So the loss function that we used was a cosine similarity loss, where both the language and the image features were forced to align to be parallel.
This is a learning process. I thought it was an inference process. Okay.
Yeah, no, the previous work is much more closer to inference.
Okay, thank you for the clarification. Basically, we have here vision and language and also action, physical action. So we have to start somewhere.
Yeah.
In all your demonstrations and experimental results, what was the primitives that you started with? I was wondering.
So
maybe you start with some primitive actions represented in predicate logic or something, or
So in let me start from the
right.
I'll go a little bit back. So
okay.
Start playing the demo. So give me 1 minute. I'm going down. I'm going the other way. So in the first talk that I gave that was using LTL, the predicates were completely specified. So in this case, the predicates, you completely know this side of the world. You know what finally means and you know what green means. That's known.
Okay.
Okay.
So the
green
primitives were learned already.
They weren't even learned, they were specified. So we took the map of the world and we said that this part has the symbol GR. Now you take a natural language command and you map it to that symbol GR. Right, so finally green, that part of the world will satisfy green. Right, so over here the predicates were all pre-specified in this work. So then I was like, well, specifying the predicates is the hard problem. In the object embedding case, so I'll also answer it over here, the actions are pre-specified. So whenever you see the robot picking up an object, it already has the policies to pick up the object. It's not like it's relearning those policies or anything like that, right? So the picking up options are pre-specified. We just don't know which object it is. So I'm trying to answer your question by saying it's different for different problems. In some cases, the actions are pre-specified. In some cases, the predicates are pre-specified.
Exactly.
But
what I was asking is, you have used a little bit different approaches for different problems, or
I've been trying to make them as looser as possible, and the looser I make them, the simpler the problems become. So like this is the loosest case. Over here, I did not pre-specify anything. There was nothing. The robot did not know about the state of the world. The robot had not seen any action in the world previously. Everything was learned from the data that was collected on the fly. And then we learned, we basically used a planner to plan each behavior, but all the sub-goal conditions were learned. So this is the most loosest problem definition that there is. This basically has the least amount of assumptions. The problem is that scaling it up becomes really hard. So you have to start somewhere, and that's why I went back to pre-training. So like the rest of the work now then has pre-training of like the Q-value functions and stuff like that. So you learn the actions or the predicates previously, like over here, and then I'll map language to now continuous predicates. They're not even discrete.
And then while you are performing, did you try also learn incrementally?
So one of these works is incremental. The Andrew Hunt paper is incremental, and so there is an incremental learning paper in here. I don't talk about it too much. Not this one, but the one that my student is working on right now, that's an incremental learning problem, because over there he's teaching objects, that one. Over here, he's teaching the object in the learning process, so it's in the loop.
Right, that may be very important, I think.
Yeah.
Okay.
Yeah.
Good.
Yeah.
Okay. Okay. Thank you. Do you have any more questions?
Yeah.
A very short question. So, it might be a bit not close to today's presentation, but I was wondering, after you show the demonstration, giving a robot several lines of commands, turn right, go forward, and wondering that, so in reality, when humans make a conversation, they make some mistakes. They forgot some comments, right? But for robots, it is not possible. But what happens if we kind of miss one comment? For example, if the precise comment is turn right, go forward, and turn left, but we forgot turn right, then it fails, right? Then would it be possible to kind of
So
learn leniencies?
in that domain, no. So in that problem domain, the robot will basically translate it into the predicates that you specified. What the robot might run into is that you told it to take a left at the end of the corridor, there was no left, right? So the robot will turn left and then it would just stop because there's nothing to do. The plan has just finished. Like it can't do the next thing. You won't even satisfy the precondition of entering that corridor, right? So it doesn't have this this very Bayesian quality of doing inference. So if I told you to take, let's say you're driving on the highway, I tell you to take the third left. Okay, you go there. So I tell you to take the third left before you come to some shop or something like that, and you are like, there are only two lefts. There is no third left on the road. So there's some misinformation that I specify to you. So now you can do two things. You can call me on the phone and be like, hey, there's no third left, what the heck do I do? So you can ask for correction. The other thing that some people do, you might turn around and take the second left. And then you might go and see, oh, does the second left satisfy my constraint of finding this particular shop, right? So in this case, the robot's not doing either. It doesn't have a Bayesian model of the world where it's kind of updating its prior based on some information that it's getting to create a new posterior. So it's something that I've thought about. It's not in that pipeline. It's very, this is what I've told you and this is what you'll do. And that's a hard question. Like the question that you're asking is not that trivial to solve. It's not like I can just, it's not like it's specified to a deep learning pipeline that I'll just do it or something like that. You need like the actual Bayesian information. You need a model of the world that you can update.
Thanks.
Okay. Oh. Okay. Last question.
You can shoot me an email. My email address is my initials, ng@asu.edu.
Thank you for your lecture. I think your research can help the industry field people work with robot with just natural language interaction, and it must be very efficient if you can make it. But for now, is obviously the performance of those research thing is not good enough to be adapt to the field, obviously. And when do you think it can be adapted to the field? Like the performance can be good enough?
I was working with Konica Minolta at some point, and we were trying to like see what kind of things are useful. So even just goal specifications with language is pretty useful because people don't have to run to a computer terminal and push buttons to say this is where the robot's supposed to go. It's even useful for like safety reasons. So you can just say stop, the robot will stop. Stuff like that where you can't go somewhere and you want to control the robot remotely. So even if you can add a little bit of the capability, right, which you can do already, like this is not like something that's like too far. Like at least safety constraints and things like that, specification with language could be added. It's not very hard to do. If you want like rich language behaviors, that would depend on a case-by-case basis. It's almost like every application will become its own research problem. So if you want to control a robot in a workshop setting, you can specify that problem and you can solve it. it might change if the type of workshop switches. So if you change the robot on the workshop, if you change the type of objects that you are shipping out of this this workshop or anything like that, any minor change, and you might have to update your model. So they're very brittle. LLMs might help with that, but it's the skills are also brittle. The object representations are brittle. So it's just a hard problem to solve from a learning perspective. So right now, people are at least specifying them discretely. So I can tell you what this object is. Can you map language to it then? That can be done.
Thank you.
Good. Thank you all for coming. We'll end our talk here today. Yes.